What if I want two congruences to hold at the same time, modulo two different numbers? I'm looking for one x, well, one family of x's, so that that x is 3 modulo 5 and 1 modulo 3 at the same time. I want both of these at the same time. When we need two of these to happen at the same time, this is part of a large, nice theory, which is called the Chinese remainder theorem. This helps us to find how to solve these kinds of questions for any numbers I put in. Not just 3 mod 5 and 1 mod 3, but I could even do 4 mod 5 and 0 mod 3. Any two things I put here, I want to know how to solve this kind of equation in general. Let's look at this with a diagram that puts a lot of numbers in the same place. I want to learn what things look like modulo 3 and modulo 5. So let me start drawing numbers. I'm going to start with 0. Actually, when you do a lot of this kind of number theory or this kind of math, it's helpful to start from 0, because 0 is 0 times everything. So I'll write down 0, 1, 2, 3, 4. What I'm going to do with these is underneath them, I'm going to write down two numbers. The first one in red is what it is mod 3. And the second number, which I will write in green, well, I'll write in blue, is what the number is mod 5. Okay? So here, I will just start and say 0 mod 3 is 0, 1 mod 3 is 1, 2 mod 3 is 1, 3 mod 3 is back to 0 again, 4 mod 3 is 1. And let's say what is the other number. The other thing is what it is mod 5. And that will just be 0, 1, 2, 3, and 4. Okay? You may now see why I chose to write 0, 1, 2, 3, 4 all in a line, because at least the 5s are nice. It's just going 0, 1, 2, 3, 4 across. The 3 is not so nice. But I'm going to now keep writing this with columns. So I'm going to write down all my numbers like this. The next one, 5, 6, 7, 8, 9. Again, I will first write down what it is mod 3 and then what it is mod 5. Mod 3, it will be 2. And then mod 3 on the 6 will be 0. Actually, you already maybe see a nice pattern. It goes in red 0, 1, 2, 0, 1, 2, 0, 1, 2, 0. It's good. 9 is 0 mod 3. You also probably see another nice pattern. If I see what it is mod 5, it will just be, the columns will be the same, 0, 1, 2, 3, and 4. That's why I wrote them, so that they would go every 5 in a row. Every row would be 5. Let's keep drawing this. Next, after 9 comes 10. So 10, 11, 12, 13, and 14. Okay, now how much red is there? It is always going 0, 1, 2, 0, 1, 2. So here's the 0, and then 1, 2, 0, 1, 2. Okay? For the blue, which are the mod 5s, it will do, again, 0, 1, 2, 3, 4. Let's do the next row. For the next row, I'm actually going to draw a double line here. For the next row, I will have my 15, 16, 17, 18, and 19. The reds, as usual, go 0, 1, 2, 0, 1, 2, 0, 1, 2. I finished with a 2, so I'll start with a 0. 1, 2, 0, 1. Now, the blues will go 0, 1, 2, 3, 4. But why did I make this double line? I made the double line because this pattern is now going to repeat again. If I look at this row and this row, and just look at the reds and the blues, they're the same. 0, 0 is 0, 0. 1, 1 is 1, 1, and so on. 1, 4 is 1, 4. There's a good reason why it repeats. The reason it repeats is I'm going mod 4 and I'm going mod 3 and mod 5. What that means is that at the least common multiple between 3 and 5, least common multiple between 3 and 5, which is actually 3 times 5, which is 15, after that point, all of my counting by 3s and counting by 5s will start over again, back at 0, 0. That's why this is a block of 15 numbers, 15 pairs of numbers. Now, looking at this picture, I see a few interesting things. One is that whatever my answer is, whatever my x is, x plus 15 will also work. Remember my original question. In my original question, I wanted an x which had both of these at the same time. What that means when I look at my picture is I want something that has 1, 3. I can look for that here by circling it with 1, 3. I see it here. So this is an x that will work. But because of this, what this means is that not only will this x work, every 15 this will work. So the answer to my question is that x is congruent to 13 mod 15. There are a few things we need to talk about now. The first is, how do I know that there will be a 1, 3? How do I even know that there will be 1? Oh, and the second question is, how will I know that there aren't more than 1? Both of those are very important. Let's start looking at this. So I already know that in these 15, there's going to be a repeat. It's going to go from here, and then same picture, and then same picture. But how do I know that this happens here? Let's look at this 15. Actually, all of these are different. 0, 0 is here. There's no more 0, 0 in this 15. Here's 2, 3. There's no more 2, 3. Here's a 0, 1. There's no more 0, 1. Over here, in these 15, every possible thing appears exactly once. What do I mean, every possible thing? For the red, there are 3 possible reds, 0, 1, 2. And for the blues, there are 5 possible blues, 0, 1, 2, 3, 4. So there are 15 possible combinations, and everything is here. So now I need to explain. Now I need to explain why everything appears exactly once. Why in 0 to 14 does every, I'll write it this way, x for red, y for blue appear exactly once. This is a proof type question. There's a theory here that we need to talk about. But it's going to also be a good way to review a theory idea that happened earlier in this mini course. If I need to show that everything appears exactly once, how many of these are there? There are 15 possible. 15 possible. How many spaces are there? There are 15 numbers that I'm checking. Here there are 15 numbers. So all I have to show actually is that nothing appears more than once. if I prove that no pair xy appears more than once, well then, since I have 15 possible and 15 places, and nothing happens more than once, well then everything happens exactly once. Everyone appears exactly once. So now my goal is to prove that if I look at the numbers 0 to 14 and I check what they are mod 3 and mod 5, I just need to check and show that I can't have two of them appear. One of them appear twice. Let's see. Suppose for contradiction that I have two squares in this table. One square is A, and here's another square, which is B. And both of these are in the first 15. Okay, they're in the first 15. And suppose that I have the same x, and also they have the same y. I need to prove that this is impossible. Well, let's think. The fact that they have the same x, what does that mean? That means that if I look modulo 3, A is congruent to x modulo 3, meaning that if I divided by 3, the remainder would be x. I also know that B is congruent to x modulo 3. Well, what that means is that A and B are congruent to each other modulo 3. Aha! Now it gets interesting. You see, if A is congruent to B modulo 3, that means that the gap between A minus B is divisible by 3. I'm using this notation. 3 divides the gap between A minus B. Okay. But the same logic also tells me that since A and B are congruent modulo 5 with y, I also know that A is congruent to B modulo 5. What that means is that 5 divides A minus B. Okay, now if 5 also divides A minus B here, then I have A minus B is divisible by both 3 and 5. And since A and B are both divisible by 3 and 5, and that 3 and 5 are relatively prime, okay? Since I have that these two, 3 and 5, are relatively prime, there's no overlap between them, 3 and 5 relatively prime, then that tells me that actually both 3 and 5 divide this, and so it's 15, which divides A minus B. Oh, this is like an argument, an idea we had earlier. If I have that 15 divides A minus B, well then A minus B should be at least 15. But A and B are in the space where the maximum difference between A and B is only 14. The maximum difference is 14, which is less than the 15. And so what that means is that I cannot have two different A and B that make this happen. This is my contradiction. I cannot have two different A and B because I simply do not have enough space. So that's my contradiction, and I'll draw my contradiction mark here. So what have we shown? with this argument, we now know that if I have this red x, blue y, meaning what is the number modulo 3, what is the number modulo 5, inside this first block of 15, you will see everything at most one time, But our argument says, since I have 15 of them to throw there, and none of them happens more than once, and there are 15 spaces, I actually get everything exactly once. So that's how I know on this problem. That's how I know for sure that there is one of them. So I know that no matter what I'm trying to solve, no matter what x, y I'm trying to put into here, no matter what those congruences are, I'll always be able to find one. That's one thing I want to say. The other thing I want to say is what was so important about 3 and 5? This 3 and this 5. What is important is not that they are prime. Where we used anything was that they were relatively prime. The important thing about these two is only they're relatively prime. For that, let's look again at the whole argument to see why. In here, it doesn't matter that it was 3 and 5. I could draw a picture like this with anything and anything else. But the repeating happens at the least common multiple. Now, if they are relatively prime, their least common multiple is their product. Even if I had 8 and 21, the repeating is at 8 times 21. Okay, so this part doesn't care that 3 and 5 are prime, only that the least common multiple is the product. That's important because the amount of space I have, this 0 to 14, this is the product of the two numbers. Okay, and the product of the two numbers here is the same as the number of possibilities there. If I had 8 and 21, the number of possible pairs is 8 times 21. Then this is the same. I just want to show that I have nothing up here more than once. And finally, when I look at this picture here, I will find that both the 8 and the 21, both of these numbers divide the gap. But the gap size is less than the product of the two numbers. So what I wanted to say is, even though I gave this example with very specific numbers that we can understand just by looking at it, it works for any two numbers which are relatively prime. For the last punchline, though, I do want to say these numbers were chosen intentionally. The answer here is 13. 13 is an interesting number. It's considered unlucky in some cultures. But 13 and 15 are related. 13 is the same as minus 2. This is just an observation to share with you in case you see a problem like this anywhere in your experience in the future. You see it's minus 2. Well, that's interesting. I could have guessed that. Because in this problem, I'm supposed to find x is congruent to 3 mod 5. This first equation is actually the same thing as an equation x congruent to minus 2 mod 5. The second equation, 1 mod 3. That's the same as an equation x congruent to minus 2 mod 3. Can you think of an x which is minus 2 mod 5 and minus 2 mod 3? Maybe minus 2 would work. So you can know immediately that minus 2 is a solution. So from just this, you can actually figure out that x is minus 2. And if you know the Chinese remainder theorem, you know that there will be a unique solution which is mod the product of those two, which is 15. Not every problem can be solved this way. Only a few can. But the reason I wanted to use this to explain is we were able now to explain the whole Chinese remainder theorem, prove it, handle non-primes, and even share a trick at the end, which if you want to do these questions fast, can be helpful.